Welcome. Let's take a look at our Chapter 2 Mechanics preparation. So we're going to be dealing with graphing some quadratics here. So we're going to end up with some parabolas. And you know a little bit about this. One thing we know is quadratic formula tells us that x equals the opposite of b plus or minus square root of b squared minus 4ac. And that's all over 2a, but I'm going to put this over 2a and this over 2a, so that's a little bit of a switch. But if we think about this for a minute, that's when this finds the values when the equation is set to 0. So if y was equal to 0, here, this would give us our two zeros where the parabola passes through if there were two zeros. And one of them would be at negative b on 2a, and then to the right plus this value. And one would be at negative b on 2a, and to the left, this value. So it stands to reason that this is the center of our graph, or our vertex of quadratics lies at negative b on 2a something. So, problem number 1, I'm going to find the vertex first. Negative b on 2a would be my x value would be the opposite of b, the opposite of negative 2 over 2 times a 1, or it's at 1. And I'm going to use a 1 value t-chart for this. How nice is that? I'm going to put in 1. I get 1 squared 1 minus 2 times 1 minus 2. So I get 1 minus 2 minus 1. I get negative 2. So my vertex is at 1, negative 2. Now, our normal old parabolas we've talked about, plain old x squared parabolas go over 1, up 1, over 2, up 4, over 3, up 9, over 10, up 100. So from here we can just build our parabola. Over 1, up 1, over 1, up 1 from the vertex, over 2, up 4, and over 2, up 4, and that's all that fits on there. What we want to avoid is having this look like a V down here. So we start at the parabola and come out of it flat. So it looks more like a U. We come out of here flat just for an instant, so it looks more like a U, and it doesn't have that sharp corner. So there's our parabola. So what do we do when we have parabolas that aren't like normal old parabola? Let's take a look at number 3. I'm still going to go with x equals the opposite of b, that's positive 18, over 2 times negative 3, negative 6. X is negative 3. So my tiny little t-chart, xy, put in negative 3. Now let's see here. Can we do some of this in our head? I get negative 3 squared 9 times negative 3, negative 27. I get negative 3 times minus 18 plus 54. I'm going to come back and talk about those two things. And I get a minus 26. When you do this, if you've gotten the right negative b on 2a value, this number and this number will always be opposites, one positive, one negative, and this will always be double that. So it's just a good way to check if negative 3 was our true location of the vertex. So here we combine these. I've got negatives, a total of negative 53 combined with the 54. This is just 1. So at negative 3, 1, I have a vertex. Now I want to come back to this problem in just a second. There's one more thing I wanted to mention about number 1. If we go through a y-axis, if our parabola goes through the y-axis conveniently, for instance at negative 1, that should be pretty reassuring. Our graph should look like negative 1, and then should look like it has a slope for at least a little bit as it's going through there of negative 2. And then ultimately a right side up parabola. So that's pretty reassuring. If I was to do that backwards, I would say, wow, by the time I'm over here at 0, I should be all the way down at negative 26. That's on this problem. By the time I get over to 0, I should be all the way down at negative 26, which doesn't fit on our curve. Okay, normal old parabola goes over 1, up 1. Not this one. This is negative 3 times normal parabola. So instead of over 1, up 1, we're over 1, down 3 times 1. 1, 2, 3. Instead of normal old parabola, over 2, up 4, we're over 2, down 3 times 4, down 12. So from 1 down 12 gets me all the way down to here. And there's my mirror point. Again, even though it's sharp, I'm still going to come out of here for an instant level. I still don't want to have it look like a V. And so now, if I go back and I check, it at least seems reasonable that I'd be down 26. Let's think about that for a minute. If I went over 3, normal parabola over 3 up 9, this parabola over 3 down 3 times 9, 27. If I'm at 1, it would be at negative 26. And it is going through that point very, very steeply down here. Negative. So feel pretty good about that one. Okay, one more quick one here. Go through this quickly. X equals the opposite of B. Negative 6 on 2 times A. 2 times negative 1, negative 2. X is 3. So I put 3 in my tiny t-chart. Whoops, there's X. Here's Y. Put 3 in my tiny t-chart, and I get the opposite of 3 squared plus 6 times 3 minus 13. Here's a common mistake. This is not negative 3 squared. This is the opposite of 3 squared. Exponents are lazy. This 2 does not have to overextend to that negative. It's only affecting the X here, only affecting the 3 there. So I get negative 9 plus 18. Take a look. 9 is half of 18. I've got 1 negative and 1 positive. Minus 13. Negative 9 and negative 13. Negative 22 versus positive 18. Negatives win by 4. 3. Negative 4. Regular old parabola, over 1 up 1. This is upside down but regular. Over 1 down 1. Regular old parabola, over 2 up 4. Not this one. Over 2 down 4. Flat coming out of here, so it doesn't look like a V. Okay, so I think we're going to be in pretty good shape on those. Let's look how this changes when I get an inequality. Everything starts out the same. My X value of my vertex is the opposite of B, negative 16 on 2 times A, negative 4 or 4. My mini t-chart, put in 4. Let's see, what do I get? 16 times 2, negative 32. What should I get here then? The opposite of this, positive, double this, 64. Let's see, put in 4, sure enough, plus 64 minus 34, which really tells me that this just equals 32, but positive. And 32 minus 34, negative 2. So 4, negative 2, upside down and double, over 1, down 2, over 2, usually up 4, but now over 2, down 8, mirror point, and then I am allowed to be equal to. So, solid line. If it was strictly less than, it would be a dotted line. And then this says, I want y's where they are small. And small y's are down. So any point on here, I want to be shading below that. So our shading occurs inside. Okay. Similar. X is the opposite of B, negative 2 on 2 times A. 2 times negative 1/2 is negative 1, giving me an X value of my vertex at positive 2. I put 2 in, what do I get? 4 times negative 1/2, negative 2. This should be positive 4. Double, but opposite. It is plus 2, so I get positives of 6 versus negatives of 4. Or 2, excuse me, 6 minus 2, positives win. 2, 4 is on this curve. Regular old parabola goes over 1 up 1. Not this one, over 1, down half of 1. Regular old parabola goes over 2 up 4. Not this one, over 2, down half of 4. And now take a look at the point we just got. This point right here, that's reassuring, goes through 2. This is reassuring as well, has a slope, fairly steep slope, Let's see, do I have room for another point? Normal old parabola over 3, up 9. This one should be over 3, down half of 9. 1, 2, 3, 4 and a half. Had room for it. Okay. Nothing to it. All right. Sorry about that. Got off center here a little bit. Number 11. Solve each by completing the square. To complete the square, the first thing we're going to do is we're going to divide out any common factor we have. And we have a common factor in here of 9. So I can divide both sides of this by 9. And I get v squared plus 2v minus 72. Not minus 72, that's silly. Divided that by 9 minus 8. My fault. Okay. Next, to complete the square, I want to group my v's on one side, and you could probably do this in one step. Do these first two. V squared plus 2v equals, add 8 to the other side. And now I'm going to invent something. What I want, if I have a lead coefficient of 1 here, and that's our goal, we're going to get a lead coefficient of 1 there somehow. Sometimes we have to be creative. This time it was pretty easy. I want to take b, put that over 2, so it goes b over 2, b just so happens to be 2, and I want to square that. And that equals 1. So here's b on 2, gives me 1 squared is 1. And I want to put plus 1 here. But this is the important part that gets forgotten. That 1 did not exist. So I was balanced. V squared plus 2v equals 8. But I added 1 here, so I'm going to add 1 there. This will become a factorable perfect square if we do this right. And this is v plus 1 squared equals 9. Therefore, v plus 1 equals plus or minus square root of 9. V plus 1 equals plus or minus 3. So v equals, subtract 1, plus or minus 3 minus 1. 3 minus 1, 2. Negative 3 minus 1, negative 4. Okay, that's it. All right. Not crazy about this because I don't really want that 2 there. I'm still going to get rid of it. I think I'm going to divide everything by 2 first. I get p squared plus 8p plus 19 halves equals 0. I'm going to follow the same process. I want to isolate my p's on one side, leave a blank, subtract 19 halves on the other. I can't reduce by anything conveniently here. I had to divide by 2 though because I wanted a 1p squared. So I take half of 8, 4, half of 8, square it. That gives me 4 squared 16, that's plus 16, but I have to add 16 over here as well. Well, plus 16 is, of course, plus 32 halves. So I had to balance that step. Why do I do that? Because I've just created a perfect square. P plus 4, if we FOIL, you can check it, we get this. And that gives me 13 halves on this side. So solve for P. P plus 4 is plus or minus square root of 13 on 2. That is P plus 4 is plus or minus, we're going to rationalize denominators, square root of 2 on square root of 2, I get square root of 26 all on 2. And if I subtract 4 on both sides, final answer, P equals negative 4 comes over, joins a plus or minus square root of 26 on 2. And that's what we would get if we go through quadratic formula. Just another process. And some of you will choose to stick with quadratic formula at times, given the option, but there is definitely a place for completing the square. So hopefully you can follow those, come up with some solutions on 12 and 14. I'm going to jump down to number 17 here. If you can handle 17, you can most certainly handle 15, 16, 18. I'm going to group all of my v's on one side. So I'm going to subtract 6v squared because there's more v squareds over here. If this was 9v squared, I'd subtract 7v squared. But I'm going to group my v's to the left. And that gives me subtract 6v squared, a single v squared, add 5v's to negative 12v's, negatives win by 7, leave a blank, and subtract 6. So everything's accounted for. I subtracted 6v squared out of here, added 5v out of here, and subtracted 6 out of there. So I need half of my b term. This isn't the most convenient, but we have to deal with it. Negative 7 on 2 squared. So that is 49/4, and I'm going to put that right in here. That's my invention, though. It wasn't there, so I balanced that. If the left side was equal to the right side and I added this to the left, I have to add that to the right. This should be a perfect square. We may check this one. That would be v. It would have to be minus, and the square root of 49/4 is 7/2 equals negative 6 plus 49/4. I'm just going to make this negative 24/4 plus 49/4. Or what do we get there? We get 25/4. That's kind of convenient if you're looking ahead. So v minus 7/2 equals plus or minus square root of 25/4. 5/2. If I add 7/2 to both sides now, I end up with v equals 5/2 positive plus 7/2, 12/2 or 6. Negative 5/2 fighting against positive 7/2 gives me 2/2, 1. Okay, turned out pretty nice. All right, let's take a look at a little bit of advanced factoring. If we're going to factor and we have 4 terms, and we're supposed to factor this, always, 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 we look for the greatest common factor. I can take x's out here, 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 but I can't take them out of there. So I can't take a number out of here other than 1, so I can't factor anything out, the greatest common factor. So we're going to go ahead and factor out by grouping. And I'm going to try it by grouping these two together. Out of these two, I can get an x to the 4th. X to the 4th times x squared, get me back to x to the 6th, minus 5, that would get me back to, if I distributed, negative 5x to the 4th. Now here's the biggie. Some people show this a different way, but I like this. There is no sense in factoring by grouping unless I can match this. Can I get an x squared minus 5? That's the big question. Well, to get an x squared, I have to factor out negative 9. Does that work? Negative 9x squared plus 45, it does work. Now, if I think of this, if I thought of this as just a, x to the 4th a, minus 9a. I can factor an a out. Well, my a is just a big mess, but I can factor that big mess out. X squared minus 5 times x to the 4th minus 9 equals 0. Now this says factor, but we're clearly solving with an equal to 0 here, so we're going to continue this and solve. To solve this, either x squared minus 5 equals 0, or we can factor this again. This is a perfect square minus a perfect square, and the difference of perfect squares factor like this: square root of x squared plus square root of 9, square root of x to the 4th, x squared, plus square root of 9, 3, times, repeat those, x squared but minus 3. Okay, if 3 numbers multiply to be 0, then one of them is 0. Either x squared minus 5 is 0, or x squared plus 3 is 0, or x squared minus 3 is 0. So either x squared is 5, or x squared is negative 3, or x squared is positive 3, or x is plus or minus square root of 5, plus or minus square root of negative 3, or plus or minus square root of 3, none of which simplify. And plus or minus square root of negative 3, there is no number times itself, no real number times itself that multiplies to be a negative, so this one is eliminated. So we end up with, careful here, not 2 answers, we end up with those 4 answers. Okay, let's take a look at another one. I can't factor x's out, it has no x's. I can't factor a number out, they only have 1s. So I'm going to group, take out x to the 4th, I get x squared plus 1. A quick distribution check, x to the 6th plus x to the 4th. Which means over here, it's worthless if I can't get x squared plus 1. I don't know. Well, to get x squared from negative 25x squared, I've got to take out a minus 25. Does that work? Negative 25x squared, distribute, minus times plus, minus 25, it works. Factor this whole package out, and once that whole package is factored out, I've got x to the 4th minus 25. So either x squared plus 1 equals 0, or this guy equals 0. But once again, perfect square minus perfect square. X squared and 5, x squared and 5, plus and minus. If the number times a number times a number equals 0, then either x squared plus 1 is 0, x squared plus 5 is 0, or x squared minus 5 is 0. So x squared could be negative 1, x squared could be negative 5, or x squared could be positive 5. But x squared in real numbers cannot be a negative. X squared cannot be a negative. So I'm left with rescue the squared, x equals plus or minus square root of 5. That's our solution. Now, one kind of cool thing to do on this would be take your graphing calculator and graph this. And I don't know what the whole graph of this looks like, but I know on that graph, at square root of 5, somewhere between 2 and 3, probably a little bit closer to 2, there would be zeros on there. And the graph would wiggle through somewhere or another. We're going to come through that point, and we're going to pass through that point as well. So that's a good way to check on these, and we will pick it up from there on part 2 of this video series. Good luck.